All right, let's look at another example. This time, we're going to study something more complicated because we have a motion, not only in a circular motion, but also there is another dimension that's perpendicular to the circle that we have to deal with as well. And it's called a conical pendulum. What's a conical pendulum? Well, basically we have this string and we attach an object, small object at the end of the string. That's called a pendulum, right? If we swing it, if we swing in the plane, we know how to, we have seen that before in dimensional analysis. But we're going to do something different with this pendulum. We're going to set it, we're going to pull it to the side, and instead of just let go it by itself, we're going to give it a horizontal push, okay, a horizontal push, so that it settles into a horizontal circular orbit like this, circular path like this. And then the string will sweep out a cone, okay? That's called a conical pendulum. Let us analyze the motion of this pendulum. The object, the bob at the end of the string, is our system. And we have drawn a free body diagram, simple enough to draw. Non-contact force mg, contact force the tension. These two forces do not add up to zero, obviously, as you can see here. As a matter of fact, we don't want to add up to zero because it is doing a circular motion in a horizontal circle. So obviously, there has to be a net force providing you with a centripetal acceleration, right? So let us look at how we analyze this problem. You know, it does a circular motion in a horizontal direction, okay, in a horizontal plane, that is. It does not move up and down the vertical direction. So there is no acceleration in the vertical direction, and therefore, what is the net force in the vertical direction? Well, that's got to be zero, right? That's got to be zero. So let us figure that out first. What happens in the vertical direction? You know, this angle is theta, so is that angle. That angle is also theta, right? In the vertical direction, we must set the net force to be zero. So you have a tension which has a vertical upward component, and how much is that equal to? That will be adjacent versus the hypotenuse, right? So that will be T times cosine theta. And there is also a downward gravitational force. This is upward, that is downward. They must cancel each other out, so that must equal to mg. That's how we balance out, so that the object has no acceleration vertically. Okay, that's one thing. Another thing is that in the horizontal direction, the net force is not equal to zero because it actually does a circular motion in a horizontal direction, which requires a centripetal force. So let's look at the horizontal direction. In the horizontal direction, mg has no contribution, okay, because it's totally vertical. But the tension does have a horizontal component, and actually you can see that component is going in and happens to be pointing toward the center of that circle, right? And how much is that component? Well, that will be that component, like this, from here to there. That will be T sine theta, right? T sine theta. That is the only horizontal net force. mg has no horizontal component. Therefore, it must give you the horizontal force needed for moving in a circle in a horizontal direction, that is the centripetal force. Okay, so how much is the centripetal force equal to? That will be equal to m v squared over r. What's r? R is the radius of the circle. Okay, r is related to theta as well as the length of the string, which I call L. Okay, if the length of the string is L, then what is r equal to? Well, look at this right angle triangle here, right? We have opposite versus hypotenuse. So really, what is r? R is just L times sine theta, isn't it? Okay, so let me rewrite it. That is m v squared equals divided by L sine theta. Now, what am I looking for? Well, I can solve, for example, at this point, I can eliminate t. I got two equations, right? And I can solve for v. I can figure out how fast it moves. But I can also find the time it takes, okay, the time it takes for this guy to complete one revolution. That is the period of the conical pendulum. Let's look at how we calculate that. So instead of v, let us find the time it takes. Okay, you know the circumference, the distance covered in one revolution is 2 pi r. So we got 2 pi r. And what is that equal to? Isn't that equal to v times the time it takes to go around, let's say t. That t is the time it takes to complete one revolution. Okay, we can, instead of solving for v, we can solve for t now. we got enough equations. The easiest thing to do to eliminate t, the tension, is to take this equation divided by that equation. Okay, then t is gone. Then I find an expression for v, plug that v in here, I can solve for t. Alright, let's see what do we get. So, after we do a little simple algebra, this is what we get. We get v equals square root of lg sine theta times tangent theta, and t, the time it takes for one revolution, equals 2 pi times the square root of l divided by g times cosine theta. We can take a look at some special cases, like we always want to do, to see if it makes sense. Okay, look at the case, look at what happens when theta increases. You know, when the thing moves, the speed of its motion has to do with the angle, right? If you push it harder initially, it's going to settle into a higher circle, which means theta is greater. So common sense tells us that if you really want to go fast, you have to use greater theta. And that makes sense. You see, when theta increases, sine and tangent, they both increase. So v will increase as a result. As a matter of fact, what happens when theta goes to 90 degrees? Oh, that's the highest possible value for theta, right? When theta goes 90 degrees, this thing, the string is pretty much horizontal. You see, the string is horizontal. What's that telling you? That means tension is almost horizontal. And v, according to this, goes to infinity because tangent at 90 degrees is infinity. Okay? So, in order for the thing to move in a horizontal circle, with the tension being horizontal itself, with angle theta equals 90 degrees, it has to move at infinite speed. Okay, how does that make sense? Well, as a matter of fact, it makes sense because look, the tension is almost horizontal. Let's say it's not quite, but let's say the angle is 89.9999 degrees. Okay, whatever, it's just a little bit shy of 90 degrees. Then the tension is almost horizontal. There is a tiny, tiny component vertical. But that tiny, tiny component still has to cancel mg. Otherwise, the thing is going to go up and down. Okay, that means even a tiny, tiny component of tension is enough to cancel with mg, which means the tension is humongous. It's extremely large. When a tension is extremely large, t is almost infinity. That means v is almost infinity, right? Because t and v, you know, they're related like this. That means v goes to infinity. That makes sense. Okay, it also makes sense what happens when theta equals 0. When theta equals 0, this thing is just dangling there. It's not doing anything, right? So what's the speed? 0. Okay, the speed is simply equal to 0. That's when both tangent and sine goes to 0. Okay, you can also understand qualitatively what happens to the period t. In fact, when theta goes to 90 degrees, cosine theta is 0, which means t is equal to 0, which means it takes almost 0 time to go around. That makes sense because the speed is essentially infinity when that happens. Okay, of course it takes no time to go around. That is the so-called conical pendulum.